Hello, guys. Welcome back. So, today we want to start a new chapter, which is going to be chapter 5 prime in my slides, and it's basically chapter 5 of your textbook. And we're going to talk about some standard models for dynamic systems. So, what are the chapter objectives? So, you guys noticed that in chapter 2 to 5, we went after modeling a single energy domain. Yes? So we talked about modeling in mechanical domain, in electrical domain, in hydraulic domain. We mixed the energy domains, okay, as electromechanical, hydromechanical, hydroelectromechanical, and so on and so forth. Now we get to a point that we have a mess of differential equations, okay? They are all over the place. We don't know what to do with them. So in this chapter, we want to understand how we can break down those mess of differential equations into an elegant and beautiful format, which is consisted of first order differential equations. Okay. And basically, we call it as state space. Okay. How we can transform the dynamics of the system, okay, into state space, which is an elegant format of showing the differential equations. And what's that? The state space, one more time, it's basically a state of first order differential equations. So at the end of this chapter, one of the things that you're going to learn is how you can break down a higher order differential equations to a bunch of first order differential equations, okay, or make a first order differential equation system, okay, and then solve those differential equations at the same time. Also, we're going to talk about another standard model to represent the dynamics of the system. So the first standard model was state space. Another the standard model is basically transfer function and input-output relationships. So I'll teach you guys how you can actually go from state space to input-output relationships, and then from input-output relationships to transfer functions, and also basically your way backward from transfer functions to state to input-output relationships and to state equations. Okay, so in a way, I'm not going to teach you guys anything new. Okay, I'm just going to teach you guys how you can present your dynamics. Okay, how you can present your dynamics. And like I said, these three are standard form for presenting the dynamics of the system, which means that when you pour the dynamics of your system in state space or in input-output relationships or in transfer functions, okay, they act like a common language among system engineers. Yes, so engineers here in the United States, engineers in Russia, in Europe, in China, in Africa, okay, all over the world, they're going to look at your dynamics and they're going to make sense of them. So this is one thing. The other thing that we are going to spend some time on it, okay, is how we can right now solve those differential equations. We look at some numerical solutions for your differential equations using MATLAB and Simulink, okay, and also we look at some hopefully analytical solutions for your differential equations. At the end of this chapter, I'm going to talk about block diagram, okay, which is basically a graphical method to represent the dynamics of the system. Okay, with that, let us start this chapter. State variable equations. Somehow we talked about state variables before, okay? So for instance, when we were talking about the order of the system, let's say that the order of the system was number 2. The system was second order system. We mentioned that if the system is second order system, it means that the system has two independent variables that we need them to describe the dynamics of the system. And we call those two independent variables as the states of the system. Okay? So state variables, okay, are in fact some physical variables, like what? Like displacement, like velocity, like voltage across your capacitors, like currents through the inductors, okay, like the pressure in the tank, okay, or the volumetric flow rate in a pipe. There are some physical variables that you need them to describe the dynamics of the system with them. Okay? There are some requirements for the state variables. First thing, the textbook definition for a state variable is in fact the smallest set of dynamic variables that can completely define the characteristics of the system. Which means that you shouldn't have redundancy in that smallest set. You see what I'm saying? Okay, so when some people say that you are dealing with the smallest set, it means that you shouldn't have any redundancy in there. Okay, in other words, if you pick one state as X, okay, the next state cannot be 2X. Why? Because X and 2X are not independent from each other. They are basically linearly dependent. You multiply 2 by X, you get 2X. Yes? So one requirement for your state variables is that it should be the smallest set, which means that the variables that you pick should be linearly independent. So this is something that you need to be careful about it. For instance, if you pick the velocity as one of your state variables, then momentum cannot be the next state variable. Why? Because if you multiply velocity by the mass, which is a constant number, you will get momentum. Yes? So you cannot have both state variables as velocity and momentum. It's not possible. It's not there. And same thing with the energies. Okay, if you have one of the state variables as, for instance, the displacement, you cannot have the potential energy of the spring as this displacement, because you can calculate the potential energy of the spring if you have this displacement. Another thing to note is that state variables are not unique, guys. Okay, for instance, I prefer to pick velocity as the state variable, okay, and someone else said that, okay, I do not like velocity, I'm gonna pick the momentum as my state variable. Okay, that's okay. They're not unique. As long as you're not picking velocity and momentum at the same time as your state variables, you should be okay. Okay, so just keep an eye that these state variables are not unique. So there are some standard conventions for state variables. The first thing that we use is we show states with X, and we show the inputs or the controls with U. Now, if I have one state, it's X. If I have two states, it's going to be X1 and X2. If I have three states, it's going to be X3. Okay, X1, X2, X3. So you see that the indices, the sub-indexes, they come after X. Okay, and this is the standard convention. Similarly, for the controls, if you have one control, it's U. If you have two controls, they're going to be U1 and U2. If you have three controls, they're going to be U1, U2, U3. You see that? The sub-indices are going to be added when you have multiple states and multiple controls or multiple inputs. Normally, the number of states, we show it with the number n. N as in Nancy. And normally, the number of controls or the inputs, we show it with the number R. Yes? In fact, in your textbook, they're going to show it with R. Okay, so you have R number of inputs and N number of states. Okay, so now we can formulate the problem. The state variable equations or the state equations are in fact a collection of N number of first order differential equations. Okay, that together they describe the dynamics of the system. So for instance, if you have x dot 1, okay, then on the left hand side, then you have some processing function f1, which is processing your states x1, x2 all the way down to xn, and all your inputs u1, u2 all the way down to ur. Similarly, you will have x dot 2, another processing function. Similarly, x dot n, another processing function. Okay, so with the number of your states, which is n, you're going to end up with first order differential equations, which are here. Now, there are things that I want you guys to pay attention here. Okay, first, you see that on the left hand side, you only have states. You do not have, the time derivative of your states. You do not have states, you do not have inputs. On the right hand side, you only have states and the inputs. You do not have any time derivatives. You see that? Okay. Now, these processing functions that I'm going to circle in red, F1, F2, all the way down. If all of these guys are linear, then your system, the overall system is linear. If only one of these guys is nonlinear, then your whole system is nonlinear. In fact, if every term in every one of these guys is linear, besides only one term that is nonlinear, that small nonlinear term is going to make your whole system nonlinear. Okay? So it's easy to see nonlinearities and linearities in the systems. Okay. Most of the time, guys, you have no other choice than solving these differential equations at the same time together. Why? Because most of the time, these differential equations are highly coupled to each other. Okay, they're linked to each other. They have components in each other. Okay, so you need to solve a system of first order differential equations at the same time. And for that purpose, we're going to rely on numerical solvers such as Ranch-Kutta. Okay, there are times that it's possible to work with analytical solutions. However, this format specifically, we call it as state space equations or state variable equations, or in general, state space, a space of first order differential equations. This format is absolutely amazing for numerical calculations. Okay, basically, you make your state space, okay, and you dump it in MATLAB. MATLAB will use Ranch-Kutta, okay, to solve those differential equations at the same time. Okay. Now, state space are nice, okay, and we're gonna work with them in a bit, okay. However, before going there, I just want to do a little bit of math refresher for you guys, just to refresh your memory about matrices and vectors. Okay, so a vector, let's say X, is a stack of elements. Yes, is the stack of elements on top of each other. So this is x1, this is x2 that are stacked on top of each other until xn. It means that n components in this vector are stacked on top of each other. In high school, we show the dimensions of a vector by the number of rows, here is n, and the number of columns, which is 1. Yes? In college, we do a little bit of a better job. We say that, okay, we say that the state X belongs to a set of real numbers, which means that each component in X, such as X1, X2, all the way down to Xn, they are real numbers, okay? And the dimension of this guy is n by 1. And most of the time for vectors, since 1 is redundant here, we show it with Rn. It means that this is a vector with n number of elements. And all elements in my vector are in fact real numbers. This big R here shows a set of real numbers. Okay, for instance, if I have X as 1 and 2, then my X belongs to R2, which means that it's going to have only 2 components. And each of these components are going to be a real number. Okay? How about matrices? Well, matrices are a little bit more involved than vectors. So if you have A, then for instance, this is going to be a 1, 1. This is going to be a 1, 2, and all the way down to a 1. M. Yes? Similarly, this is going to be a 2, 1. This is going to be a 2, 2. Okay, sorry, 2, 3, 1. Okay, and this is going to be a, let's say, n 1. Yes? And similarly, you can go ahead and fill the rest of the elements in the matrix. Yes? So you will have a n by m here. Okay? And if you want to show the dimension of this matrix, it's going to be A is in fact in R, number of rows here, which is n, and number of columns here, which is m. Good? Okay. And this shows that every element in this matrix, like the ones that I'm circling, it's a real number, okay? And the dimension of the matrix is given to you like this. As easy as this, yes? Okay, now, when it comes to matrices and vectors, what we need to do in this course, or what we need to learn in this course or know in this course, is being able to do matrices algebra. What are matrices algebra? Okay, let me just get rid of these guys here. Matrices and vectors algebra, in fact. Okay. What are the matrices and vectors algebra? They're gonna be summations, subtractions, and a little bit of inverse and those kind of things. Okay, and also multiplication. Okay, let's say that for the sake of an example, let's say that I have matrix A as 1, 2, 3, 4. The dimension of this matrix is 2 by 2, and I have matrix B as 5, 6, 7, 8. Again, the dimension of this matrix is also 2 by 2. If you want to add or subtract two matrices to each other or from each other, okay, you have to have one specific condition. What's that specific condition? The size of two matrices should be exactly the same. So you cannot add a matrix of different size to another matrix with different size. Okay, so their size must match. Their size must be the same. Okay, and this one is easy. If you want to add A and B to each other, okay, then each respective element would be added to the other one. So A, respective element in A 1 and 5 will be add to each other. Then another one is 2 and 6. They're going to be added to each other. Okay. Then another one is 3 and 7. They're going to be added to each other. And at last, you're going to have 4 and 8. They're going to be added to each other. Good? As easy as this. Subtraction is also super easy. If you want to subtract matrix A from B or B from A, okay, you're going to subtract the respective elements from each other. Okay, so for these guys, I'm just showing with them with a black marker. Yes, so A minus B would be 1 minus 5 for this element, which is going to be negative 4, 2 minus 6, which is going to be negative 4, 3 minus 7, it's going to be negative 4, and 4 minus 8, it's going to be negative 4. Good? As easy as this. So subtraction and summation or addition is not a problem. Most of our problems with the matrices are basically the multiplication. Okay? So let's say that you want to multiply matrix A and B. Okay, so let me just get rid of these ones. Okay. And at this point, I want to multiply matrix A and B. Okay, so I would like to find A multiplied by B. Okay, and this multiplication is 1, 2, 3, 4, which is your matrix A, multiplied by 5, 6, 7, 8. Okay, now here you need to be a little bit careful. Yes, so when you multiply, the first element here is going to be multiplied by the first element here. The second element would be multiplied by the second element here. Okay, so in fact, the first row would be dot product or dot multiplied with the first column. Okay, and if you do the math here, this is going to come out as this is going to come out as 1 multiplied by 5 plus 2 multiplied by 7. Okay, and you guys know that 1 multiplied by 5 is 5, 2 multiplied by 7 is 14. Okay, and 5 plus 14, this is going to be 90. Yes. Similarly, the second element over here, this is going to be the first row here multiplied by the second column. Okay, so it's going to be 1 multiplied by 6 plus 2 multiplied by 8. Okay, next one. This row would be multiplied by this column. So this is going to be 3 multiplied by 5 plus 4 multiplied by 7. Okay, and the last one would be the last row of the first matrix multiplied by the last row of last column of the second matrix. Okay, so this is going to be 3 multiplied by 6, okay, plus 4 multiplied by 8. Okay, and this is going to give you the resultant when you simplify. Okay, there are things that I want you guys to pay attention. When you multiply two matrices to each other, the number of columns of the first matrix and the number of rows of the second matrix must be the same. Otherwise, it's not going to be possible to multiply those two matrices with each other. Okay, this is very important. The number of columns of this first matrix should be equal to the number of rows of the second matrix. Also, the resultant matrix, the dimensions are going to be borrowed from the first and the second matrix. Okay, the number of rows of the resultant matrix comes from the number of rows of the first matrix. Or number of rows from A, okay, and the number of columns of these guys from the second matrix. Okay, so the resultant matrix have the number of rows from A and the number of columns from B. For instance, if in this example A was a 2 by 2 and B was a 2 by 1,000, okay, then A multiplied by B would be in 2 by 1,000. Okay, why? Because the number of rows comes from the first matrix and the number of columns comes from the second matrix. Note that, guys, if A was 2 by 2 and B was, let's say, 3 by 100 or a 3 by 1,000, this multiplication was not possible from the beginning because the number of columns and rows of these two guys must match. Okay, must match for you to be able to multiply these guys to each other. Okay. Okay. So very important, yes. Next thing is a determinant of a matrix. Okay. For a determinant of a matrix, let me just get rid of these ones as well. Let's say that your A is a 2 by 2 matrix, okay? And I'm going to do a 2 by 2 because anything more than 2 is going to be a little bit difficult, okay? And I do not want you guys to do it by hand. But let's say that your A matrix is A, B, C, and D, okay? The determinant of A, sometimes we show it with absolute value of A, okay? Is going to be the, for a 2 by 2 matrix, is going to be the multiplication of the elements on the main diagonal, which is AD, minus multiplication, so this is the main diagonal, yes, minus multiplication of the elements on the off diagonal, yes, or the other diagonal. So this is going to be minus BC. This is your determinant. We're going to use determinant a lot, okay? So it's going to be main diagonal minus the other diagonal. Okay? And the other thing is, if you are lucky and your determinant is not 0, then your matrix is not singular. For a matrix that's not singular, you're going to have a matrix inverse. Okay? And for that matrix inverse, we show it with a 2 by 2 matrix. It's going to be A inverse equals to 1 over determinant, yes, multiplied by another matrix. For this matrix, the main diagonal, you're going to swap them. So this is going to be DA. The other diagonal, you multiply them by -1, C negative B. Okay? And you guys know that for a 2 by 2 matrix, this is going to be AD minus BC. Good? AD minus BC. Okay? And this is one formula that I want you guys to remember. How you can find the inverse of a 2 by 2 matrix. How you can find inverse of a 2 by 2 matrix. Okay? With that, I'm gonna go and solve some examples, okay, and see how we can find the state space dynamics okay, for a system.